everybody. This is Yanhua. I'm presenting you my thesis defense, metallic nanoparticle ink formulation, development and optimization for electrohydrodynamic inkjet printing. Let's get started. This is a brief sketch on HD printing, which is we're actively research the HD printing basically using hydraulic force as well as electronic force to push the ink liquid out of the print nozzle, which can create a smaller droplet, which enhance the printing resolution. For evaluation characterization, we're using high-speed camera and microscope to discover the features as well as the printing dynamics during the printing process. So this is the total structure on what I'm going to talk about today. We'll first talk about the backgrounds, give you several introductions on the mechanism of this application, as well as some basic background information for evaluation and characterization. After that, we're going to jump into materials, which we have several material factors can impact on this process. Since we're impacting on the process, what kind of process we can control electronically as well as the geometry of the actual printing. After that, the printing performance are being evaluated both for the resolution as well as some functional performance such as X-ray or height stacking performance. So let's go to the background. So we're going to introduce you some backgrounds on inkjet printing, UHD printing, fluid dynamics, as well as X-ray shielding and materials attenuation. So for inkjet printing, first we initially to create the inkjet printing as so-called continuous printing, indicated here. For continuous printing, what we have is the droplets continue to deposit on the printing substrates. If they did not, there is a separate mechanism to collect all those unwanted droplets into the recycle process. However, this recycle process creates a lot of troubles, so the developers start to think to reduce or to create another process that do not require this mechanism, which is coming to the droplet on demand type of methods. These methods are only produce droplets while it required. So there's no waste of ink droplets. Later on, there are two different mechanisms or two different types or styles that for DOD printing. One is vapor or thermal, one is piezoelectric. For thermal, the ink need to be vaporized to create a bubble, so the ink can be pushed out to form the droplet. Otherwise, there should be piezoelectric materials to induce acoustic mechanical waves that to ejecting the ink droplets. Those materials, those methods are developed by HP, Canon, Epson, and Brother. Again, later on, depends on the requirements of the resolution of the inkjet printing. We need higher and higher resolution, so HD come out. Both thermal and electronic or piezoelectric DOD are based on hydraulic pressure. No matter what's the vapor pressure or the mechanical wave, it's hydraulic. However, if we need additional forces, electric forces come into play. So we have computer-controlled pressure regulator as well as voltage signal generator. With a amplifier, we have enough voltage to control um, the electric potential accumulated on the tip of the nozzle. Then, with the nano positioning system as well as high-speed camera, we can capture images when they're actually printing. So this is what happened on the tip of the nozzle when actually printing happens. So a electric signal come in with certain voltage and certain materials property, a single droplet less or smaller than the nozzle can be created and deposit on the substrate. Later on, we can examine it by a microscope. Why HD? As previously we mentioned, increasing the printing resolution as well as did not require the materials to be able to vaporize, such as thermal DOD, they need to be vaporized. And for piezoelectric DOD, they have certain limitations on viscosities. We don't have that. And we can do fast prototyping. So for small features, which is why DOD come into play. For fluid dynamics, so this is a typical guidelines on materials properties, how the materials property can come into play for ink formulation design. There are two significant numbers. One is Weber number, one is Reynolds number. Those two numbers are being used to guiding the formulist to design the ink. Typically, for traditional inkjet printing, DOD or continuous inkjet printing, the Z number, which is 1 over OH, here is the OH definition, need to be smaller than 10 or larger than 1. However, with additional forces, electric force, we can expand this 10 limit into 14. For my formulation, most of the cases are exactly on the line of 10, which is creating a tricky situation where those inks are specifically for EHD printing, not suitable for inkjet printing, or it's risky to try on inkjet printing. And this is a schematic on how X-ray shielding and material attenuation come into play. So with a typical atomic structure of a materials, we have a lot of spaces around the nucleus between this atom to another. So there are several different scattering mechanisms or types of X-ray scattering happens when the X-ray hitting matter. Then, since we have the K characteristic peaks, so for each materials we have at least 2 K alpha and K beta to have this spectrum where this is your acceleration voltage, how high the voltage you apply on the X-ray tube. So therefore, this is a unfiltered photon energy X-ray spectrum that you can get when they using whether or not it's a directional tube or transmissive tube. So this is a schematic on how do the calculation. So the intensity ratio, which is IZ over I0, is linear proportion to the thickness, which is Z here. However, if we have printing on the substrate, we can use the substrate intensity as I0 to eliminate the differences between the substrate I0 to the absolutely zero. There is no matter, or in our case, since we're not perform this in a vacuum, so this is basically air condition of attenuation. So with the ratio mechanism, um, the calibration is not needed for the differences between the glass slides and the air. So let's jump into chapter 1, where we are talking about the materials. So my study is basically focusing on two materials. One is silver, one is tungsten. So let's get into it and see what's going on inside of the materials. So ink formulation, what materials we're putting in the ink and how to synthesize the materials and what modification we're do and why we need to do those modifications. For silver, so this is a typical process that we're coating PAA, which is polyacrylic acid, two cans of polyacrylic acid onto our silver, which is the silver metal are reduced from silver nitrate. After that, it was sonicated and washed and extracted by ethanol, since ethanol is not a welcome solvent for PA-coated silver. So we can precipitate out all our silver particles, and after several rounds of centrifugation, we can have our particles. So this is a typical DLS evaluation on the size as well as the zeta charge. So also confirmed by X-ray, our average particle size is 180 nanometers. Next, we'll talk about solvent. So without the liquid, we cannot carry all those particles to use as a fluid to perform inkjet printing. So we need to find a proper solvent. There are two choices. One is TGME, which is typically used in inkjet printing design. The second one is the MSO. For the MSO, being a well-known solvent for most of organic matters, as well as some biological substance, which is later on we can use this type of solvent system to perform bio-grade printing services. As you can see in the microscope image, that the MSO are a better dispersion compared to TGME, which is a better choice in our case. Why not water? Water is a good solvent, and it's recommended by the original publication. However, water is not suitable for EHD printing because water is really easy to vaporize. They have a lower vapor pressure and lower boiling point compared to TGME or DMSO, which creating a problem when it actually be printed. The water formulated ink can be clogged on the tip of the nozzle, which creating unstable printing performance. For surface tension modification, we're looking into different types of surfactant. Here's a chart that typically we're using neutral surfactant and positive and negative, which is here. Tritinex is it's a nutrient. SDS is a negative. D-tab is a positive surfactant. As you can see, for here the Tritinex, all of them are really good to reduce surface tension at 10 to the -2 mole per liter. However, consider this environment we're getting into. Silver is actually a negative um, charged or negatively preferred particles, which here D tab is not an option because if you're introduce D tab, it will aggregate. SDS may be okay, maybe not. However, when I actually perform the experiment, SDS creating a clogging um, problem when they actually print, it will evaporate as well as creating bubbles. So that's not good. So then leave the Triton series. Um, so how we evaluate the surface tension number? So we're basically using image J that have a particular algorithm that we can calculate the surface tension based on the surface droplet pendant method. We're using high-speed cameras to capture the last image. The droplet leaves the tip, and we can use that as a reference to calculate the actual surface tension. So for different Triton necks, we have different HLB value, which is how the surfactant likes water. So as we can see, when the HLB value increases, the surface tension increases since it's like water. But the viscosity is slightly also increased. We don't want that. What we want is actually only changing one parameter, in this case surface tension, and do not changing viscosity, do not changing dielectric constant. So this is not an option. So for viscosity, what we have is we're using glass reel. Since glass reel are 2 or 3 orders of magnitude higher than water, what we need to do is to adding really little amount of glass reel so they can dramatically changing the viscosity. As we can see, from 0 to 5%, we are changing viscosity from below 4 to almost 8. However, the glass reel also changing the surface tension as well as the dielectric constant quite a bit when we above 5%. So what we're careful to do is to only introduce glass reel less than 2% to control the shift, the surface tension shift, while we still have a quite large of area of viscosity difference. For permittivity, which is how much the charge it can carry in a single droplet. Um, it it depends. It also make a difference when they're actually flying in from the tip of the nozzle to the substrate. So we need to consider that most of the charges accumulated on the surface of two different interface. So what we are doing here is to introduce more silver particles that creating more interface, which here you can see from 30 to 40 percent of silver increase, we're dramatically increasing the dielectric constant by a force of the magnitude. However, we also increasing the surface tension as well as the viscosity. So we need additional surfactant and glass reel to reduce the changes while we increasing the silver content. So this is what the finally come out. So with this, so for S1, S2, S3 is control surface tension, while other dielectric constant as well as the viscosity doesn't change much. For viscosity, we have V1, V2, and V3. For dielectric constant, also so-called permittivity. So here is the P1, P2, and P3. For tungsten, so when we actually purchase the tungsten particles, um, it does not distribute at a small range. So you can see in the TEM images, um, there are particles big as 500 nanometers, as well as some particles may less than 10, which is not good. So what we need to do is to creating a mechanism or creating a process to classify all different sizes of particles. So based on some pattern we found online, centrifugation is a really good method. However, we need to discover what kind of liquid or dispersing liquid that can carry the weight of those particles. So I did a little bit design on um, using ethylene glycol and glacial to design a mechanism, have a tunable viscosity for my dispersing fluid, and with that we can using um, centrifugation to test what kind of process varies the performance. Which here I'm varying the speed, varying the centrifugation time, as well as the viscosity. However, the viscosity does not make quite a difference. However, the speed make the biggest differences. So the speed is the actual matter of the control. With that, I was able to separate into three different sizes of the particles. Um, while they have different viscosities as well as different zeta size and zeta charge. Um, so, with all the particles or silver and tungsten particles being separated, being synthesized, we're walking to process. So, what is actually we're focusing is how to get the droplet smaller than a tip of the nozzle and deposit onto the substrate. So again, the silver as well as the tungsten being introduced. For silver printing, as you can see in the images, we have different samples. We can print dots, we can print lines, we can print circuits, we can using confocal microscope to actually scanning them and find the heights of the printing parts. For dots, we need to evaluate how stable the printing gonna be. So what we have here is a 300 microvolts print on a 26 nozzle. This here is a DC print without any signal generation. We can still have a 12.5 micrometer diameter average, plus minus 1.16, with an error rate of 9%, which is less than 10, to confirm we have a stable print. On the B chart, this is a strain gauge reliability test and pattern design, how fine or how dense we can design the lines so we can have a high strain gauge gauge factor sensor we can produce. So here the line spacing is 500 micrometer. We can still increasing this until it collapses. Don't forget this is two-layer print. And C and D is a tentative design on how well it can print. Without that, so the differences between the lines are 550 micrometer, which is we can control the pattern's resolution less than 50 micrometer. For confocal microscope images, we can see when the printing a crossover on top of each other, they're creating a higher height of the actual print. So which indicate the ink or the printing performance is stackable. So the more layer you print, the more height you can stack it onto. So there are several printing parameters we can control. So here's a schematic on what kind of signals that we can do. Previously, this is it's a DC, so here is AC. So we have a frequency we can control how fast this cycle can have per second. So we're basically using hertz. For a total cycle time, there is a portion that we perform a high signal, or here is a signal that higher than 100, higher than 0 volts. That since the silver is well into negatively charged, um, these high signal volts are decharging time for the surface of the substrate to remove the excess negative charge, enable for the silver to deposit on. Since the negative charge is the active time, so the high voltage are evaluated to are designed to evaluate how deep this valley is, which means how much of energy the silver particles have been charged. With that, with all those three control variables, we can see with the voltage differences, we can have a quite differences between the diameter. However, with the frequency change, um, the power law fitting lines does not have a higher um, impact factor. However, with the duty ratio, which is how much charge for each cycle, it do change a lot, which is 0.95, which is almost equal to 1. That's much, much higher impacting than the frequency. We also varies the viscosity, surface tension, as well as the dielectric constant of our inks. So this is different inks formulation, but we keep the condition at the same. With that, so we can see with the viscosity increases, our droplet size, or the printing feature size, or the resolution, the size are increasing, which is the resolution are decrease. That's due to the droplet is or is not willing to elongate it while being energized. With a high viscosity, it does not willing to be elongated, which is to drag more liquids out when the energy being introduced into the droplet. For surface tension, so um, basically the process is to break the surface tension, or to create another surface, which is need to introduce energy to overcome the surface energy, which here, when the surface increasing, when the surface tension increasing, the droplet decrease. So that also makes sense, because when we have more and more surface tension density, which is here surface tension, um, certain amount of energy required for a smaller droplet are same as a bigger droplet if the surface tension are small. So we're creating a balance or equilibrium between the surface tension density as well as the surface energy that can be introduced per droplet. For a dielectric constant, with higher dielectric constant here in the yellow bar or the green bar, depends on the projector, that with higher dielectric constant, it requires less silver, or less volume for the charge deposit to overcome the surface tension, well, which makes sense here. The droplet size are decreased. We also introduce the we also perform a multi-layer print. Basically, what we do here is to print different layers of the silver onto the substrate, see how wide they can spread. So make be careful. This is a non-waiting time print, so there is no waiting time between layers and layers. So when the next layer of droplet deposited onto the original droplet may not be fully dried. So what we have is when we're increasing our number of layers, we are increasing the width, which needs to be justified because when we actually produce sensor, we need to have a wider spread or a lower line density because we don't want this line and that line to be shorted so our function can be properly functional. Then we're characterizing tungsten droplet. For tungsten droplet, we're using high-speed cameras to capture images. Um, specifically, we're focusing on the behavior when they're hitting the substrates. So here are those parameters that we can capture. And here's the process how the machine or a computer code can process. This is the angle, this is the width, this is the height. So finally, for each droplet, we have those four data lines. For different cases, for gravity and gravity only and gravity with the electric forces, which mimic our HD actual printing, the droplets are elongated before they hit the substrate. So with that, we have three different types of particle size formulated ink. This is the image like summary on how the droplets are hitting. Obviously, this is a circle, so which is this is the performance well without the electricity. With all those data, we analyzed those. So we discovered that the phase duration and height of the droplet increases while increasing the particle size. Formulated the ink, both on the gravitational fields and the electric field. That makes sense. Well, a larger particle that are less responsive compared to smaller because they have a large momentum. So the time responding time are quite large, and since they occupy a large volume, so the heights are also large. For a large particle sized ink, it also results in a large diameter. As we mentioned, they have a larger volume and under gravitational field, but the smaller diameter and an electrical field, which here is the explanation. So a large particle that it have a smaller surface to mass ratio, which in the same particle content level, a smaller sized ink, smaller sized particle formulated ink have a larger interface area that can carry more charges, which here have a smaller diameter. For a droplet with the medium particle size have the highest impact initial velocity in the three particle sizes. This may due to both the surface as well as the viscosity. So if the viscosity are too large for let's say the large particles, it does not willing to move, which make the viscosity smaller. However, for a smaller particle size, they may have a large impact on the electrical force. However, it also have a smaller size of the droplet, so it may inevitably feel the electrophores smaller, which also due to the resistivity of the air, since we're not printing in vacuum, I also feel the resistance. So it also decreased the velocity. For chapter 3, we studied the performance, how printing parameters impact the printing, how materials parameter impact the printing. So here's are the charts that for different numbers of printing, the widths are increasing. For different numbers of layers, the thickness increase. See the differences between 2, 5, and 10 plotting speed. The higher the plotting speed, the thinner the line can leave on the better. We're also doing some calculation to analyze all those data and to unify it with this data points to see how much it can stacking, how high of it can stack while it print on different speed and different layers. So we can see the more layers you print, the less stacking efficient you can get. The higher the printing speed, the less stacking efficient you can get. For tungsten printing, with increasing the voltage, you can see there is a increase in the particle size. With increasing the frequency, the particle size does not changing that much. It's similar with the silver behavior. Here is the active time, which is less the time is the less the duty cycle is, which is tungsten particle are able to charge in positive, which is the bigger the duty ratio, the bigger the droplet, which is giving more time to charge. So here, increasing the active time, increasing the particle charge. So we're printing different layers, and then you can see the different heights and width. We measure the thickness is 12, 20 is the 3, and then we're using this to convert the thickness to the grayscale ratio. This is the actual measured ratio and convert to also for bulk tungsten and the same thickness. This is the bulk tungsten grayscale ratio. We can compare the bulk tungsten have a lower ratio, which indicates have a higher stopping power. For conclusions, ink properties impact on the printing performance, such as viscosity, surface tension, and dielectric constant. Printing parameters impact the printing performance, lets the voltage, the duty cycle, and the frequency. Even though the frequency does not impacting that much, it also is still impacting on it. Both ink properties and printing parameters impacts functional performance, as we can see the stacking rates as well as the X-ray attenuation. Further characterize electronic conductivity of the printing silver lines are needed, since we're going to produce sensor. Optimize the packing density of printing tungsten lines are also needed, since we want to improving the shielding efficiency of the printing tungsten. Optimize the condition of reduce the printing resolution for both tungsten and silver. So we want to find a better condition that print finer and finer features that can be applied on some applications, as well as high aspect ratio of microscopic parts for functional electronics. So we're looking into stacking higher stacking ratio while they print. With that, I would like to thank you for your attention, and I can take questions.